In this video, maximum subarray sum using Kadane's algorithm would be discussed. In the previous video, in previous two videos, you would have discussed the same problem, maximum subarray sum, using two different methods such as brute force method and dividend conquer method. With the brute force method, we achieved the time complexity of big O of n square, and with the dividend conquer method, we achieved the time complexity big O of n log n. So when you compare the brute force and dividend conquer method, the dividend conquer method gave us the less complexity than the brute force method. Now let's check whether any other method is possible, like which is going to give you the lesser time complexity than the brute force method and dividend conquer method to identify the max subarray sum. Yes, it is there, which is the Kadane's algorithm only. Using Kadane's algorithm, you would be able to identify the maximum subarray sum with lesser time complexity. This Kadane's algorithm is an efficient technique used to find the maximum subarray sum within a given array of integers. So basically it solves a problem in linear time complexity. So Kadane's algorithm solves a problem in linear time complexity, making it efficiently faster than the brute force method and the dividend conquer method for larger arrays. This algorithm works, this Kadane's algorithm works by iteratively traversing the array and maintaining two variables. One is max so far and another one is max end. Let's see the example, and this is the pseudocode for Kadane's algorithm, which is a very simple, straightforward pseudocode it is. This is the pseudocode and this is the example. Let's trace the pseudocode and solve the example step by step. This is the given example. The example array contains totally 7 elements. Two variables we are supposed to maintain. It would be iteratively traversing the array, maintaining two main variables. One is max end, one main variable is max end and second main variable is max so far. Now we are using a loop here in the pseudocode. The loop starts from 0 till n, which means till end of the array. The very first step is we are supposed to find the max end. To find the max end, the formula is max end plus array of I. Array starts from 0, so current I value is 0, which means it would be focusing array of 0. Array of I is array of 0. Before we start working on this algorithm, working on this problem, we have to set max end as 0 and max so far as minus infinity, because it has the combination of both the positive and negative integers, so I am setting it as minus infinity. Now calculate max end as the first iteration. During the first iteration, when I is equals to 0, max end equals to max end plus array of I. Max end is already 0, 0 plus array of the current max end plus array of I value. Current max end value 0, current array of I is array of 0, which is minus 2, so max end value is minus 2. After identifying the max end, we are supposed to compare array of I with the max end. If array of I is greater, then only max end value would be updated, otherwise max end value would not be updated. So the condition is only when the current array value is greater than the current max end value, the max end value would be updated, otherwise will not update. Now check current array of I value and current max end value. If it is greater, you update the max end, otherwise you no need to update the max end. It is same, both are same, so you no need to update the max end value. Go to the next if statement. Check max end is greater than max so far. Max so far is minus infinity, max end is minus 2, which means max end is greater than max so far, so we are supposed to update max so far as max end. So now max so far is going to be minus 2. So only if the condition is satisfied, we are supposed to update max end as well as max so far. Now I equal to 0, the first iteration is over. Now increment the I value. Now I value would be 1, which means now I value would be pointing array of 1. Again identify the max end. Every time for each I value, we are supposed to identify the max end and compare max end with array of I value, and also compare max end max so far. Whichever is maximum should be retained under the max end as well as max so far. Now identify the max end value. The current max end plus array of I is going to be the current max end value, right? So minus 2 minus 1 is minus 3. After identifying the max n, check for the next step. If array of I is greater than max n, array of I is -1 and max n is -3, only if array of I is greater than the max n should be updated. So now update it as -1. Now since array of I is greater, array of I should be retained under the max n. Next, compare max end and max so far. Whichever is maximum should be retained under the max so far. Yes, max end is greater than the max so far, so max so far should be updated as -1. Increment I now. Now I is pointing array of 2. Identify the max end again. To identify the max end, we are supposed to sum up the current array of I with the current max end value. So -3 -1 is -4. Max end value would be updated as -4. Now compare max end and array of I value, which if array of I is greater than the max end should be updated. Yes, array of I is greater, so max end value would be -3 now. Now compare max so far and max end, whichever is greater should be retained as the max so far. Max so far itself is greater, so no need to change max so far value. Increment I now. Identify max end formula is adding current max end value with the current array of I value. -3 plus 4 is going to be 1. Max end value would be updated as 1. Now compare array of I value and max end value. Array of I value is greater. If array of I value is greater, max end value should be updated to array of I value, which is 4. Now compare max end and max so far. Yes, max end is greater. If max end is greater than max so far should be updated to max end, which is 4. Increment I value. Identify max end again. Current max end value with the current array of I value. If you add 4 and -2, you would be getting 2. Now compare array of I and max end. Whether array of I is greater. No, array of I is not greater than max end, so max end no need to update max end value. Now compare max end and max so far. If max end is greater than max so far should be updated. No, max end is not greater than max so far, so no need to update max so far. Increment I. Identify max end means adding the current max end value with the current array of I value. If you add 5 plus 2, you would be getting 7. Compare array of I with the max so far. If array of I is greater, you have to update max end. No, array of I is not greater, so no need to update max end value. Now go to max so far, check max so far and max end, whether max end is greater than max so far. Yes, it is greater, so update max so far. Then again increment I. Identify max end value plus the array of I, which would be 8. Max end value would be 8. Now you check array of I is greater than max end value. No, array of I is not greater than max end value, so no need to update max end. Now compare max so far and max end, whether max end is greater than max so far. Yes, it satisfies the condition, so max so far should be updated to max end. Increment I value, there is no more value, the condition would get violated because till n only it would get executed, right? Since there is no more value to get processed, whichever the value is retained under the max so far is going to be the maximum subarray sum. This is how with the Kadane's algorithm it works. So it's very simple, it's very straightforward. If you trace the pseudocode line by line, it be very easy to understand. Follow the step, each and every step for each and every iteration perfectly. Now we'll check the time complexity. When it comes to time complexity, if you check, there is only one loop we have used here. If you check this loop would get executed for n plus 1 number of iterations. Till n it is going to be the right iteration. When it comes to n plus 1, the condition would get violated and the loop would come out. So if you check, the loop would get executed for n plus 1 and all the inner statements would get executed for n number of time. So if you compute like normal operation count, if you apply n plus 1 plus n, you would be getting 2n plus 1. If you ignore the constants, finally the dominant term here is n, which means the final the worst case time complexity is big O of n. So for Kadane's algorithm, the complexity is going to be big O of n. Kadane's algorithm is very efficient with the time complexity of big O of n, where n, we all know where n is the size of the array. It is widely used in various applications requiring the efficient computation of maximum sum subarrays. If you check, so far we discussed 3 different methods to identify max subarray sum. One is brute force method with the complexity of big O of n square. Next, we used divide and conquer method. We solved it using divide and conquer method, and the complexity we achieved was big O of n log n. As a third method, we used Kadane's algorithm, and we achieved the time complexity of big O of n. If we check, the Kadane's algorithm performs very efficient way with the lesser time complexity of big O of n. We can say that it's performing better than the previous algorithm, previous 2 algorithms, brute force method as well as the divide and conquer method. Thank you.